Welcome, Algebra 3 students. We're in Lesson 9, and today we're going to finally get into proofs. And do not freak out. I've kind of been giving you some forehand knowledge and showing you, some of the things that you're going to be using, but it's not going to be a hard lesson. It's going to ease you kindly and gently into proof. Some of the proof illustrations we've had in previous years, and those lessons have been a little bit all at once and just a little too much, but this is the beginning of the year, so we have all of this time to ease you into proofs and get you doing amazing at them. So I wanted to remind you one thing that we talked about the last lesson, and that is congruency. Congruency, as we discussed before, is the geometric equal, right? So congruency is to shapes what equal is to numbers, right? So when we have two shapes that are just alike, we don't say that they are equal. Instead, we say that they are congruent. And the congruency symbol is written like this. It has this little wavy line, which is a tilde over the equal sign. And you'll have access to that in your Jupyter system. We'll put that in the special characters menu. But your congruency is when two shapes are equal to one another, we say they are congruent. We do not say they're equal. If we have numbers that are values that are equal, then we will use the equal sign. We're talking about the measure of an angle, like 52 degrees is equal to 52 degrees, right? We will use equal for that when we're talking about numbers. But when we're talking about triangle ABC is the same as triangle DEF, then we'll use congruent. Triangle ABC is congruent to triangle DEF. I hope that illustrates that a little bit better for you. So in talking about the congruency of, let's say, triangles, we have some very specific ways to determine whether or not they are congruent. And sometimes it's easy to tell. Sometimes you're looking at triangles, right? And you have one here, and it is, let's say it's a right triangle, just because that's easy. And let's say we have another right triangle that's the same size, right? This looks pretty close. And we can tell, we can look at it and we can see that this one is congruent to this one. And, these line up, right? They're all congruent. They have all the tick marks and everything. But sometimes it doesn't always look like that. Sometimes, let's say, this one doesn't have the tick mark right there, right? Let me put this line back. And it didn't go back. Let's put it back here. There we go. Or maybe this one, let's see, maybe it is, let's copy. And then we're going to paste it back. Let's say maybe it is twisted around, right? It's the same size and shape, but it's all twisted around. And it's not really obvious that these are the same triangle anymore because they've been twisted and moved and they're not on the same level. So we have some very specific rules that tell us how we can prove that triangles are congruent to one another. And we call those postulates. Do you love how I switched from print to script there? Postulates of congruency. You say that to yourself or say that to a sibling and make them, think you're really smart because it sounds pretty fancy. Postulates of congruency are the rules that we have that tell us how we can prove that triangles are similar or congruent to one another. Not similar, but congruent. So one of those, the first one is side, side, side. And we call it the SSS, which just stands for side, side, side. And we reviewed this in the geometry review at the beginning of the very first lesson, but and it's also in your Quizlet. But I wanted to go ahead and go through this, step by step. So side, side, side tells us that if we have two triangles and they have three sides that are congruent to one another, then those two triangles are congruent. So if you think about it, if you take the opportunity, let's say you take three pencils that are different lengths, right? And you arrange them in three different ways. Like you rotate them around and you try to, and then you draw around them on a piece of paper so that you have the same lengths each time. It doesn't matter how you arrange those sides. They're going to be the same triangle each time because there's only three. So there's nothing that can get in between one or the other. They're all kind of touching the other two sides. Each one touches the other two. So what you might end up with is a mirror image of a triangle, but it's still the same triangle. They're always going to be alike. So you can try and try and try, but you're never going to make those sides not give you a congruent triangle. So that's the first postulate, side, side, side. The next one that we have is called side, angle, side. That's SAS. And it just is side, angle, side. And all that means is if you have two sides that are the same length, right? Let's say 1 and 2 here, and then you have a degree of measure in between. So side, angle, side. This angle determines how far apart these two sides are from each other. That's just the way it works. The angle here determines the height or the length of these 2 points. So if you have a side and an angle and a side that are congruent to one another in two triangles, then by default, the height between this length and this length point are going to be congruent. So it gives you side, side, side by telling you that the angle in the middle is dictating what this third side's length is going to be. So now we have, that's two postulates, side, 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 angle, side. There's another one, and this one is going to be angle, side, angle. So again, angle, side, angle. And these are postulates that you do want to memorize. You do want to write these down because these are the ones that you're going to be using when we write proofs. And angle, side, angle just means that we have an angle here that is congruent to the angle here. And then we have a side that is congruent. And then an angle here that is congruent. And by default, by definition of a triangle, let's say we have a side here, right? Here's our side. And let's say we have an angle here. And we have an angle here, right? This is angle 1, this is angle 2. It's telling us how far this ray can open. This one, let me make this a little bit more in line. This one is telling us how far this ray can open, which then tells us where those intersect. So if you have an angle, a side, and an angle, these have to intersect at the same point because of the degree of measure of the two angles. This determines where they intersect, and where they intersect determines the length of each side. So if you have an angle side and an angle that are congruent in two different triangles, like this, then by default, these sides will be congruent and these these sides will be congruent. Not only that, this angle will be congruent to this angle as well, because by the very definition of the way they intersect, it's going to be the same. So that tells you another way that you can look at triangles based on the information that you're given about them and say, yes, it is congruent because of the angle, side, angle postulate. And that's all you have to do. That's all you have to say is, yes, these are congruent. Reason, ASA. So those are some things that you are going to want to write down and memorize. And that's not all of them. There's some more. But I need to make some room so I can illustrate and show them to you. So there is another one. And it is, or actually there's two. They're basically the same. And they are angle. Actually, I don't have to do the comma. You can have angle, 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 side. And the reason we have 4 here is because you could have angle, angle, angle and have similar triangles. But if you have angle, 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 side, if one side is the same and all the other angles match up, then you have automatic congruency. Just like the illustration that I gave you for angle, side, angle, the other angle is automatically congruent. So angle, side, angle, or angle, 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 side, they're really the same thing for the same reason. If one side is congruent and all the other angles are congruent, then the other two sides have to be congruent as well. That's just the nature of a triangle, which is why it fascinated Pythagoras so much, I guess. The other one that falls in line here is simply angle, side, angle, angle. Again, it's just the same one in a different order. And it's just all about the way you look at the triangle. You know, I think it's a little silly myself to have these two. You really only need to worry about angle, 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 side, because you can rotate the triangle any way you want to make it look like angle, 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 side. So I actually wrote that wrong. It should be angle, side, angle, angle. You could pretty much use these interchangeably. They mean about the same thing. There's only one more, and it's a little bit different. And this one is for right triangles only. And it is for right triangles only because it is a hypotenuse leg, right? That is the name of it. It is hypotenuse. I have to remember how to spell that. There we go. Hypotenuse leg. And by definition, only a right triangle has the hypotenuse. So if it has a hypotenuse right here, then by definition, it has a 90-degree angle. So that's a side and that's an angle, right? A side and an angle. So if it has another leg, that's technically another side. So hypotenuse leg is another way of saying side, angle, side for a right triangle. And all that means is you've got two right triangles where the hypotenuse is congruent to each other. And one of the legs is congruent. And here I've got the two different sides, but they're both congruent. So by definition, this is angle, side, side, or side, angle, side, however you want to write it. Okay. But if you have angle, side, side, which is basically this right here, then it is by definition the same postulate of congruency. We can just shorten it and recognize that it is hypotenuse leg, and by default we already have an angle that's included. We know it's a right triangle because it has the hypotenuse. So, you know, we're saying that on the front end. It has the angle and the two sides that correspond. So those are the postulates that we're going to use for the majority of the time. Most of the time we will not use, we'll use side, 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 angle, side, and then we'll typically use either angle, side, angle, or angle, 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 side. This one, you don't have to. It's the same thing. And honestly, we don't really even need that one, because if you have angle, side, angle, you have angle, 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 side. It's the same thing. So if you can write a proof using these four, and that's not what I meant to do. I meant to circle it with this and drag it up. If you can just remember these four, you can write all the proofs you need. Okay. All right, so let's begin with writing our first proof outline. Let's look at example 9.1. All right, so here is example 9.1, and we are going to do what's called a proof outline. And it's just going to kind of ease you into the idea of doing proofs. So here I have what is given, the information that we're given about our figure here, and then we have what we're being asked to prove. So before we get started, I'm going to switch colors, and you don't have to do that. That's just something I like to do to show my givens before I get started. So my givens are going to be in red. So first thing, we're told that AD is congruent to BD. Oh, and you know what? I put this in incorrectly. This is D. I was wondering why I had two C's there. That didn't make any sense. So AD is congruent to BD. So we're going to put a little congruent marker here and here. So those two are congruent. And then we're told that DC is perpendicular to AB. And that's very important, because perpendicular means that gives us a degree of measure for this angle and this angle. So we can go straight across right here. Now, because of this one line being the same, it's not explicitly told to us, but we can tell that this is the same line for both triangle ADC and BDC. So I'm going to put a marker here that shows it is the same line for both of those, and that's a circle when you have a same line that's being shared. Okay, so now we know that we have the same line here, the same leg. We have a same angle on both sides, and then we have another leg that's being shared. So they have a side and an angle and a side that are the same in both triangles. So we can begin writing that bit of the proof. The first thing you do whenever you start with the proof, the way that you want to write it, there's some very fussy and particular things that we're going to get into later. Right now we just want to get the basics. We want to just kind of get it started. So you start with your given. So you would say number one would be that AD is congruent to BD. And you always put both of them here, but you'd put them individually. So the first reason is that it's given. We're told. The second thing we know is that DC is perpendicular to AB. And we are told that also. We are given that information. So then the next thing that we know is that we have congruent triangles because we have side angle side and side angle side. That's pretty easy for this one. So we know that triangle ADC, and remember we have to write that in the proper order. So D has to go in the middle for both of these, and we have to do the outer corners first, is congruent to triangle BDC, right? and that is by side, angle, side. So therefore, we can say, number 4, that AC is congruent to BC. And the reason we know they're congruent to AC is congruent to BC is because of the property that congruent parts of congruent triangles are congruent. And we shorten that to an acronym that we can write, and that is just CP, congruent parts of congruent triangles are congruent. So CPCTC. And that is what you would write. This is a final proof. This is everything that you have to do to prove this based on this. And we only had to use one postulate to do so. But typically when we're dealing with triangles, we finalize, or we use the final result is congruent parts of congruent triangles are congruent. We know that to be a fact. So let's do one more. Let's do example 9.2. I'm going to pause and do that one for you. All right, so in example problem 9.2, our given, I'm going to use red here to indicate our givens. Our given is that angle E and angle H are congruent. So I'm going to mark those as congruent. And then EF is congruent to HG. So EF is congruent to HG. So if we see that these two are congruent, we can identify then that this has got to be an isosceles triangle because we have two angles at the bottom that are congruent to one another, and these two are the same length. So when you only have a third length to worry about, it's going to make sense that these sides then are congruent as well, because these are the same degree of measure here. We know by default the definition of an isosceles triangle is when you have two sides that are the same length, you're going to have two angles that are the same measure. And we know that these two sides right here, these two line segments at the base, are the same. So if we were to include this third one, right, then this would be equal to this as well. There's a congruency here that's just obvious. So now we have a side and an angle and a side that makes this triangle congruent to this triangle, right? I'm going to outline that for us. Let me make a smaller size. So this triangle here is going to be congruent to this triangle here. It just has to be by the very nature of side, angle, side. So let's start writing our proof. And number 1, we have angle E is congruent to angle H. And that was a given to us. Number 2, segment EF is congruent to segment HG. And that is a given. All right, so now we're looking at this right here, number 3. You don't have to put it in, but I think it's necessary in proving SAS. I'm going to put that segment ED is congruent to segment HD, and that is definition of an isosceles. I'm just going to shorten it here, put an abbreviation, and I'm just going to draw a triangle because it's easier. Definition of isosceles triangle. So then that gives me that triangle EFD is congruent to triangle, and I have to do this angle right here, the same because I put it in the middle. So that would be H, because these are the congruent angles, so those go first, HGD. And then that is going to be side, angle, side, because I have a side, angle, side, side, angle, side. So SAS property. And then therefore, DF, segment DF, is going to be congruent to segment DG, because congruent parts of congruent triangles are congruent. And that is how we would write that proof. Okay, we have one more. Let's look at it. All right, here's example 9.3. And in this problem, we're going to remember that if two segments have equal lengths, the halves of the segments have equal lengths. Okay, so we are given that AG is congruent to EF. So AG is congruent to EF. And CA is congruent to CE. And then B is the midpoint of CA. So if CA is congruent to CE, right? So these two sides are congruent. B is the midpoint of CA and D is the midpoint of CE. Then that means that this side is cut directly in half and this side is cut directly in half. And because both of these sides are the same, then all the halves are the same. So this is congruent to this, which is congruent to this, which is congruent to this. Okay? All right. So now we can begin working on our proof. One more thing. Because these two sides are the same, we have an isosceles triangle. So what else does that mean? It means that they have the same degree of measure here and here as well. We can infer that. All right, so now let's look at writing our proof. So number one, all the givens. AG is congruent to EF, and some people will write all the givens as one, which I think I'm going to do this time, just because it's a little bit faster than numbering every single line. B is midpoint of CA, and D is midpoint of C. All right, so the whole thing, this is given. It's all given to us. All right, so now I can move on to number two. And number two is we have to discuss the way we want to prove this, right? To show that BG and DF are congruent, we need to show that the two small triangles are congruent. So we have side angle side here, and we have side angle side here. So that tells me by default that I have two congruent triangles by side angle side. So that's what I'm going to do here. I'm going to say that triangle BAG is congruent to triangle DEF. And that is going to be because of side angle side. So side angle side, right? So then I can say that BG is congruent to DF because congruent parts of congruent triangles are congruent. Voila. Didn't really take a whole lot of effort on that one either. And that's all we're doing right at first with these proofs. We're going to do some very simple, straightforward proofs that are focusing on those four main postulates that we learned, and those were side, 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 right? Side, angle, side, angle, angle, side, which is the same thing as angle, 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 side. It's just, some people like to write angle, angle, side, because if two angles are the same, the third one's going to be the same, because we know the nature of a triangle, right? Some people like to spell it all out. It's the same thing. Or hypotenuse leg. Those are the four main ones that you're going to use. And so focus on learning those and being familiar with that, and you should be able to do these proofs without any struggles whatsoever. All right, that's all we have for Lesson 9. I will see you in Lesson 10.